Hello everyone and welcome back to Math Made Easy. In the previous lectures, we studied several important interpolation techniques. We started with the Lagrange interpolation followed by Newton forward interpolation, Newton backward interpolation and Newton divided differences interpolation. All of these methods have one important thing in common. They use the values of the function at the selected points. But suppose that in addition to knowing the function values, we also know the value of its derivatives also as well. For example, if we suppose we know this function at x0, function at x1, but we also know the f dash at x0 and f dash at x1, then can we use this additional information to construct a better interpolation polynomial? Yes, and this is exactly what we do in Hermite interpolation. Basically, this is a generalization of polynomial interpolation in which we match not only the function values but also one or more derivatives at the interpolation points. So today we will understand what Hermite interpolation is and why derivative information is important, and the Hermite interpolation conditions, the repeated node concept, the Hermite divided difference table, and the interpolation formula followed by the complete numerical example. So let's just begin with the basic definition. Suppose we have a function fx. So in ordinary interpolation, we may know the function at x0 as y0 and function at x1 as y1 and so on. And the interpolation polynomial is required to pass through these points. But in Hermite interpolation, we impose additional conditions as this h of x0 as fx0, h of x1 as fx1, and also this h dash x0 equals to f dash x0, h dash x1 equals to f dash x1. So the polynomial must match both function values and the derivative values, and this provides more information about the behavior of the function. Now let's just understand this geometrically. Suppose two interpolation points are given. An ordinary interpolation polynomial only need to pass through those points, but there are many possible curves such that they can pass through the same points. But now suppose we additionally know the slope of the function at those 2 points. For example, this f dash x0 becomes this f m0, and now our polynomial must not only pass through this x0 comma fx0, but it also must have the correct slope. That is this m0 at that point. Therefore, Hermite interpolation controls both the position as well as the slope of the interpolating polynomial at the specified points, and this generally provides a more constrained interpolation polynomial. Now suppose we have this n plus 1 distinct points, this x0, x1 and up to xn. And if function values and first derivatives are known at every point, then the Hermite polynomial hx satisfies this h at xi equals to fxi, and this h dash xi becomes f dash xi for I equals to 0, 1 and up to n. And since there are two conditions at each point, so we have twice of n plus 1 conditions. Therefore, the corresponding Hermite polynomial generally has degree at most 2n plus 1, and this is an important result. Now suppose we know this function value at 0 as 1 and f dash 0 at 2, and this f1 value as 4 and f dash 1 as 3, and we want a polynomial hx satisfying the h at 0 as 1, h dash 0 as 2, h1 as 4 and h dash 1 as 3. Now there are 4 conditions, and therefore we can generally expect a polynomial of degree at most 3. So let this hx equals to a plus bx plus cx square plus dx cube, and we can determine the 4 unknown coefficients from the 4 conditions only. And this is the basic principle behind the Hermite interpolation method. Now we come to an important question: how do we construct the Hermite polynomial efficiently? One method is to use Hermite divided differences, and this is where today's lecture connects directly to our previous lecture on Newton's divided difference method. And the key idea is we repeat each interpolation node according to the amount of derivative information available at that point. For example, if we know function at xi and function derivative at xi. Then we repeat xi twice. So instead of going with x0, x1 and x2, we use this as x0, x0, x1, x1 and x2, x2. So these are called repeated nodes. And this is one of the most important concepts in Hermite interpolation. Suppose we know both f at x0 and f dash at x0, we represent the node twice. This x0, x0. Similarly, if we know both function and first derivative at x1, we write as x1, x1. Then our sequence becomes x0, x0, x1, x1 and up to so on. And this allows derivative information to appear naturally in the divided difference table. Now for the ordinary divided differences, we have this function value at xi, xj as this function at xj minus function at xi divided by xj minus xi. But what happens if this xj becomes equals to xi? We would get this 0 by 0 form. So instead, the repeated node differences is defined using the derivative as this function at xi, xi equals to f dash xi. And this is the fundamental connection between the repeated nodes and the derivative information. So suppose we have 2 points here as is x0 and x1 with the function value at x0 and f dash x0 and fx1 and f dash x1. So our repeated nodes becomes z0 becomes x0, z1 becomes x0, z2 becomes x1 and z3 again becomes x1. So the table is structured as follows. We get this zi, function at zi, first difference is second divided difference and the third divided difference. So in the zi, we have this x0, x0, x1 and x1. And function at zi, we have fx0, fx0 and function at x1 and function at x1. And in first divided difference, we have f dash x0 and this function at x0, x1 and f dash x1. So the diagonal or the top entries provide coefficients for the Newton-Hermite polynomial here. And once the divided difference table has been constructed, we can write the Hermite interpolation polynomial in Newton form as well. If the repeated nodes are these z0, z1 and up to zm, then this Hermite interpolation polynomial hx becomes this function at z0 plus function at z0, z1 multiplied by x minus z0 plus function at z0, z1, z2 multiplied by x minus z0, x minus z1 plus function at z0, z1 into z2, z3 multiplied by x minus z0, x minus z1, x minus z2 and up to so on. And in compact form, we can write it as function at z0 plus summation of f of z0 up to zk, where k is starting from 1 up to m, into the product of x minus zj, where j starting from 0 up to k minus 1. And this is a Newton form of the Hermite interpolation polynomial. Now we have a question here where we need to construct the Hermite interpolation polynomial using the data as is f0 as 1, f1 as 4, f dash 0 as 2 and f dash 1 as 3. Now estimating the value of the function at 0.5. So since both the function values and first derivatives are known at each point, so just repeat each node twice. Therefore this z0 becomes 0, z1 becomes 1, z0 becomes 0, z1 becomes 0, z2 becomes 1 and z3 becomes 1. So for the zeroth divided difference, we have this f0 as 1 and f0, and similarly we have this f1 as 4. Now in the first divided difference, because the first two nodes are identically, so we have this function at 0, 0 as this f dash 0 as 2. Now calculating the value for f0, 1, we get this as 4 minus 1 divided by 1 minus 0 as 3. And for the repeated 1, we have this function at 1, 1 as f dash 1 as 3. So the first divided differences are as 2, 3 and 3. Now comes the second divided difference. So we have this function value at 0, 0, 1 as this function value at 0, 1 minus function at 0, 0 divided by 1 minus 0 and gives 1. Now next is function at 0, 1, 1 which becomes function value at 1, 1 minus function value at 0, 1 which divided by 1 which becomes 0. Now comes a third divided difference where we have to compute the value of the function at 0, 0, 1, 1 which becomes function at 0, 1, 1 minus function at 0, 0, 1 divided by 1 minus 0 and hence becomes minus 1. So now constructing the Hermite polynomial using the Newton form. So we get this hx value as function at 0 plus function at 0, 0 multiplied by x minus 0 plus function at 0, 0, 1 multiplied by x minus 0 into x minus 0 plus function at 0, 0, 1, 1 multiplied by x minus 0 into x minus 1. Now substituting the divided differences, we get this 1 plus 2x square minus x cube after the simplifications. Now estimating the value of the function at 0.5, so just substitute the value of x as 0.5, so we get this Hermite polynomial at 0.5 becomes 1 plus twice of 0.5 plus twice of 0.5 square minus 0.5 cube. Therefore, it becomes 1 plus 1 plus 0.5 minus 0.125 and hence become 2.375 and hence the function value at 0.5 becomes 2.375. Now let's just verify that our polynomial satisfies the original conditions or no. So we obtain the hx as this 1 plus 2x square minus x cube and at x equals to 0 we get h0 as 1. So this is correct. Now differentiate this hx, we get this h dash x is 2 plus 4x minus 3x square. Therefore this h dash 0 becomes 2 which is correct. And at x equals to 1 we get this h1 value as 4 again which is correct. And this h dash 1 as 2 plus 4 minus 3 as 3 which is correct. So our Hermite polynomial satisfy all the 4 interpolation conditions. Now let's just generalize it all. If we know this fxi and this f dash xi and at n plus 1 points, then we have twice of n plus 1 conditions. Therefore, the Hermite polynomial has degree at most twice of n plus 1. For example, we have the 2 points. So if we know function and first derivative at 2 points, there are 4 conditions. And therefore, the polynomial degree at most 3. And for the 3 points, we have 6 conditions. Therefore, the polynomial has degree at most 5. So in Hermite interpolation, can also incorporate the higher order derivatives. Suppose at a point xi, we know fxi, f dash xi and up to f double dash xi. Then the note xi is repeated 3 times. So the number of repetitions corresponds to the amount of derivative information available. So for example, if we have this fxi only, xi and function and the first derivative at xi comma xi, and the function, the first derivative and the second derivative as xi comma xi comma xi. So this is a generalized Hermite interpolation concept. So today we started the Hermite interpolation, one of the most powerful interpolation techniques in our numerical analysis roadmap. Unlike the ordinary interpolation methods which uses only the function values, this uses both the function values as well as the derivative values. We learned how derivative information is incorporated using the repeated notes, and the most important relation to remember is this function at xi comma xi becomes f dash xi. We also constructed a divided difference table for the Hermite interpolation method, derived the Newton form of the Hermite interpolation method, and solved a complete numerical example. We then compared this Hermite interpolation with Lagrange, Newton forward, Newton backward, and Newton divided difference methods. So our interpolation section is progressing from basic interpolation to increasingly powerful techniques. And in the next lecture, we will study the spline interpolation. So instead of trying to fit one high degree polynomial through all the data points, spline interpolation construct the piecewise polynomials, usually the cubic polynomials over smaller intervals. We will understand why splines are preferred in many practical applications, derive the basic cubic spline formulations, and solve a complete numerical example. So thank you for watching, and if you found this lecture helpful, don't forget to like, share and subscribe to MathMateEasy for the complete numerical analysis course. Until next time, keep learning, keep practicing and keep questioning, and I'll see you in the next lecture.